you do is you will place your materials in there, cut the corner off, and add 10 milliliters of water. And then just set the little pouch down in there. Such. Close it with the lid. And the reaction of that water with the contents of the envelope will generate a gaseous environment that reacts with the crystals in this little basket that's attached to the lid. And if I've got this particular envelope, it takes all the oxygen out of it. And if I use this particular envelope, it takes the oxygen out and adds CO2. You can buy these in different amounts of CO2. You can buy these in different degrees of anaerobiosis. So it's really up to you as to what type of environment you want to generate, but you can use it all in one little relatively inexpensive canister. Some of you may have noticed when we were doing the grandstand, the first week of grandstand, we had growth started on the roof. That's how I culture that organism. So the pigments, I want you to see the pigments, and of course they're anaerobic and get into life, and I had a little light set there, so we can move all those plant mass. Okay, so that particular jar allows you to create a variety of different atmospheres depending upon what you want. Now this requires you to know the cultural requirements of that organism. If I've got a Neisseria, I certainly need a candy bag. I need CO2. I don't want anaerobic. I don't want anaerobic. But it's relatively inexpensive. And many labs will have 4 or 5 of those. We've got 2. So we can do a variety of different things. Okay, last one we want to talk about is acidity. And I'm not going to spend a lot of time with it because you guys know about acidity. Talk about the pH scale. I want to remind you, because I oftentimes find that when you remind you or say something that's making you suspicious. When we talk about a change on the pH from pH 7 to pH 8, we're talking about a 10-fold increase in the hydrogen ion or decrease of hydrogen ion concentration, right? This is a logarithmic scale. pH is a logarithmic scale, minus the log of the hydrogen ion concentration. Most organisms will grow right here in neutral. 6.5 to 7.5 is the range that is typically given, and I've never experienced anything clinically that would grow typically in that particular range. There are organisms in they're in the real world, however, that are not capable of causing disease, that will do much better at high acidity. And your book talks about the organisms that oxidize sulfur. You find them in acid mine drainage, very acidic environment, and they will grow very well in pHs of 1 or even 0. And you try to grow them at pH of 7, and then die right on. Now, there are a number of fungi that do remarkably well at acidic pHs too. Have you ever wondered about the contradiction when you open up your refrigerator, open the door, and you find an orange or a lemon that has mold growing? Now, not only is that at a refrigeration temperature, but these are fruits. They're fruits that are highly acidic. They're highly acidic. Citric acid, lots of amounts of it. They grow very well. Many of the fungi are oftentimes referred to as faculty acidophile. Faculty acidophile. They would actually prefer to grow, but they will grow relatively well under modest acidity. There's not a lot that we can talk about that, well, we're not going to talk about anything that goes up toward the alkaline side. None of these causes are important in terms of causing disease or otherwise. So, we talked about oxygen, we talked about gases, oxygen, CO2, we talked about temperature and the pH. Obviously, when I make up media for you guys, I have the pH to be certain. I actually pH is about 7.2 because the autoclave, when I autoclave it, it will bring it down to about 7. Okay, so there's our terms of acidophile. These are terms that you should be familiar with. I think you already know them. They're pretty self-explanatory. Yeah, calophile, and then a neutrophile for those that prefer the neutral or the different pH. So let's talk a little bit about how we measure this growth. We've been talking about growth, you've seen growth in the laboratory. Now, how do we measure? And there are a variety of different ways that you can do this. Some are more accurate than others, some are very rapid, but not accurate. Some are very accurate but slow, take a lot of time. So let's talk about some of them. And the first one we want to talk about are those that I refer to as biomass. Those that measure biomass. And the first one, turbidimetric measurements. Turbidity. When you pick up a tube of E. coli from the prep tanks there, you never question as to whether there's anything in it. And the reason you don't question is because you can see turbidity. You may question, is that E. coli or is that D. cell? The tube says E. coli, I hope you believe it, because it should be E. coli. But you never question whether there's growth there or not, because you can see it. Well, that turbidity, that cloudiness can be quantitative along certain ranges. Historically, we've used a very simple light bulb that we would place a piece of colored plastic in front of it, a piece of acetate that is yellow in color, so as to create a particular wavelength. These are called photometers, and they were very cheap. They didn't do a whole lot, but they were satisfying, they were suitable. Nowadays, we use spectrophotometers. Everybody here, I'm certain, has used a spectrophotometer at some point of your educational life. I know you're using the chemistry, I know you're using it in the beginning biology program. Fortunately, at 105, you don't get a lab, so you probably don't have that. But in chemistry, I would imagine you have that. So you know what a spectrophotometer is. We can change the wavelength to whatever we want within reason. This is a 540 up to 70 nanometers. And we can measure the amount of light going to a sample and imposing upon a photomultiplier tube. This is a blank tube. Little word of wisdom. When I give you those rock salts, you can see them. That's because there's lots of bacteria. You know that it takes, in most cases, it takes 1 million bacteria to live before you can even begin to detect the living. And really 10 to the 6 per mil, and it will still look a little bit. That's how small these things are. And that's one of the limitations of turbidity. But here we have a clear tube. We're assuming there's nothing in it. And you can see that the light goes through it. We typically use light about 550 nanometers because that's yellow. And that matches with the yellow of our leaflet pretty well. But it goes through nothing, hitting nothing, it imposes upon, this called a photoelectric cell, it's really called a photomultiplier, but that's not important. It allows us to measure the amount of light going through. And we see 100% transmission. 100% of that light is being detected on the other side of the tube. Now, as we increase the number of bacteria or particles in that particular tube, some of them are going to begin to be scattered, and they won't go into the photomultiplier. And we'll see less numbers impinging upon it. That will result in our seeing less transmission. And as I said, within a certain range of numbers, that can be a linear relationship. Be linear. But this tells us nothing. This will tell us which receptacle has more or less, but it doesn't tell us anything about the numbers per se. This is so frequently used that you can buy a little Erlenmeyer flask that has a little side crack on it. And you know yourself, so that the fluid goes into that side arm. And you just set it right down in your spectrophotometer, take your measurement, you pull it out, get it back so it goes back into the vessel, and put it back in the incubator. So you get continuous measurement on the same sample however long you want to do it. Very commonly done, but it does have limitations because unless we have what we're going to call standard curve, we can't tell the numbers. Another way to do this is to measure We might measure the consumption of oxygen in an aerobic organism. The more bacteria we have, the more oxygen is being consumed. The larger the biomass, the more oxygen is being used. We might measure the production of a byproduct, carbon dioxide, for example. Measure the volume of carbon dioxide that's released over a period of time. And that will be indicative of the biomass of cells. If I've got X number of cells here and 3 times X number here, I'll get 3 times the amount of CO2 released and effective over here. So like I said, there's more here than there is here. Dry weight. Dry weight is probably a very outdated one, but it has been used and it is still used in certain circles. And this involves nothing more than taking your cells and growing them up in a broth, typically, although you could scrape them off of the slate. Put them into a saline solution and wash them up. And you leave a little bit of a slurry, you transfer that slurry to a free-weight cocaine. And a root, free-weight, it's called a carrier weight. You put that in there, then you allow the water to evaporate. Oftentimes it gets really dry enough, so to really dry. It's used in research for cells, but it's a measure of biomass. You can do cell counting. You can count the cells correctly. These are correct count. And there's several different ways of doing that. If you've ever had a blood work done, somebody probably told you your blood cell count. So you can count blood cells. You can use a little chamber called a hemocytometer. Well, we have this counting back here. It's called a Petkoff-Hauser counting chamber. Petkoff-Hauser counting chamber. That's a Petkoff-Hauser counting chamber. That's a dime. Give you some side reference. See that? Now what we have here, we've got 2 grids. This is a grid right here. We've got a grid over here. We have a grid here. What we'll do is we'll place a cover slip over these 2 posts. These are posts. Put a cover slip on them. And then by taking a capillary tube or a pasture pipette, a small drop, and we load the chamber. Then you allow the cells to settle down. Then we look at the microscope. We count the number of cells. Now there's a grid right there. From there to there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12 cells in that particular square. Now, if I know the dimension of that, if I know the volume of that square, I can determine the number of bacteria in my sample. I can determine it in terms of number of milliliters or the number of milliliters that I want to know. And you look through that calculation. I'm not going to ask you. It's easy to do, but I tell you, you really need to go to do it. So you really need to know how this calculation works. But it can be done. Another one that I don't have up here. This is used in the dairy industry. They all still use it. Even though those are better than. But those are a little bit closer can see that what I have here in my hand is like a large microscope. And I've got a car here that has 16 1 square centimeter polymer. Well, what you would do, and again, this is done in the dairy industry, milk. But you can buy calibrated, inoculated units. You can buy them at 1/100th of a milliliter and 5,000th of a milliliter. So I'll take one of those calibrated ones and I'll put it in my milk sample. And then, with the microscope slide positioned over the card, I will carefully inoculate, transfer to one of those square centimeters. Try to get as much of